Your next homework assignment is loaded now on Blackboard. Oh, that's not right. Monday the 31st. Could that be right? Yeah, okay. I'm always getting this class and hydraulics confused, you know. I teach them back to back, and I'm prepping for them one after another. So occasionally I just feel like a deer in the headlights up here thinking about the previous class, and then I'm teaching this one. But all right, so your next homework is due on Monday the 31st, and today we're going to talk about pond sizing, just as a throwback to what we did in class on Monday. On Monday we were playing around with StormCAD. I really like that software. I think it's great. It does a lot of interesting things, and we went through the setup and solution and annotation of a relatively simple network on Monday. Of course, that video is posted on YouTube, and I have a couple of other demos on YouTube that are linked in the homework assignment. But what you need to do in the homework assignment is design this network. So there's more inlets, more complexity, more pipes than the work we did in class. All of the data is provided that you need. It has the invert elevations for each of these junctions. It has the applicable area for each catchment, and you can identify the catchments. It's a little bit confusing because we have three different sets of lines here. There's the roadway that is indicated with these dashes, so you can kind of get a sense that this is like a couple of city blocks. There's those dashes, then there's contour lines, and these contour lines define the ground elevation, and you're going to use that to give the ground elevation to the catch basins. And then the other lines are the watershed boundaries. And so it's this dash, dot, dash, dot. Those are the watershed boundaries. And I mean, ultimately, you don't have to distinguish that or measure it by hand with a planimeter or anything, because I've given you all of the areas, the C values. Here's the time of concentration that applies to each catchment, and here's the storm data. You're going to set up a user-defined IDF table. There's way more pipe sizes than in the example we worked through. And in fact, this is probably more pipe sizes than you'd be able to find commercially. But the reason why I've added so many is I want you to have the experience of optimizing really finely to try and identify what is the minimum acceptable pipe diameter that will work for each of these segments. And so the more pipe sizes available, the more optimization practice you're going to get, where you're shooting for obviously less than 100% capacity. You don't want more water going through the pipe than its capacity, because that's impossible. But you don't want it to be any lower than it otherwise would be with really large oversized pipes. Like if you made every single pipe here 48 inches, it's not going to be over capacity, but then it would have that self-cleansing problem that I mentioned earlier. Okay, so the first part of your homework is trying out StormCAD a little bit more. The second part of the homework is sizing a pond. And so that's what we're going to learn about today. Any questions before we get into the pond and best management practices? Okay, so ponds, which we're going to talk about today, are primarily designed to help ameliorate the effects of urbanization. And flooding in urban areas occurs, I guess I was thinking of it broadly in three categories. It happens when cities are built in the wrong place, when watersheds have been changed through urbanization, and then it happens just when there's really big storms. That's when you've got flooding in cities. And I guess maybe there are some other reasons, you know, if there's a tsunami or pipe breaks. But most of the time, I think we could probably fit examples of urban flooding into these three buckets. So let me show you some pictures of New Orleans, which is a city built someplace that really doesn't make sense anymore. Have you heard before that New Orleans is below sea level? That's kind of a tricky place to build a city, right? Below sea level. And sea levels are rising because of melt of Arctic areas. You know, ice shelves in Antarctica keep breaking off into the ocean and melting, so sea levels keep going up. Greenland has just an enormous quantity of water that's melting each year, getting into the ocean and raising sea levels. And so places like the Outer Banks, where people have vacation homes that are really expensive and super nice, but are prone to coastal flooding. It's really not in a great spot for a big, beautiful house. Houston has just recurring floods all through the last decade. There have been flood after flood where some neighborhoods in Houston, people who've lived in a home maybe only 15 years have rebuilt their house or have recovered from flooding 3 times. And there's starting to be a growing appetite for just moving people out and saying, we're not going to build here anymore. It doesn't make sense to keep rebuilding in the same place, especially when this is all federally subsidized. You know, using federally subsidized flood insurance to keep paying for someone to repair their house, ultimately it may be cheaper just to relocate them someplace else. So even in California, the Central Valley of California, which is the most productive agricultural region in the world, and about 50% of the fruits and vegetables in the entire United States are from one valley in California. And they've got some flooding there because a lot of the infrastructure that was built nearly 100 years ago is starting to age. The canals, the dams can't handle the increased storm variability, and they themselves are becoming aged and decrepit. So here is a look at a big flood that happened in Huntington in 1937. I guess, you know, if we're going to point the finger at other places and say those cities shouldn't be there, doesn't make sense. It's a low-lying area. Maybe the same could be said of Huntington. You know, we're right next to the Ohio River, and in a large part the Ohio River has been tamed. Since the 30s, there have been improvements to the locks and dams on the Ohio River so that it's easier to regulate the pool level at any given time, but there are still situations where there's just simply more water than they can convey downstream. So that's why they put in the flood walls, is to prevent a repeat of this. Anybody have a guess of what street we're looking down? Kind of get a... I think that's 4th, right? With the West Virginia building there and the theater. I mean, there's definitely some stuff that's changed. I don't know that there's a store that sells candies anymore, but it looks kind of the same. Let me show you a video of the flood wall. I took an aerial video of it when they had a little bit of flooding. I guess it's just last year. Feels like longer than that. Let me show you. So this is what the flood wall looks like, and they've put these gates up. Let me increase the speed a bit so we get through this faster. I was feeling a little bit nervous with the drone because of the trees. So the flood wall doesn't have to be super thick here, just enough to hold back the hydrostatic force of the water as it rises. Ultimately, I think the water level did get pretty close, but not as high as they set the flood walls in. So this concrete wall surrounds the city to make it possible for us to live in a place that otherwise would be at threat of flooding. And if nothing else, the flood insurance for every business in Huntington would be a lot more expensive if we didn't have that flood wall. So remember, water sometimes is a precious resource, and sometimes it's a nuisance that we try to get rid of as quickly as possible. So those were all examples of flooding that occurs when construction is in a low-lying area, where the flooding is simply because the low point where the water is ultimately going is fully saturated. This flood, on the other hand, which is another picture of Huntington, the river levels really weren't that high. I mean, this water that I'm driving through is not because that's how high the Ohio River was at that point. This flooding was simply because there's too much impervious area in Huntington. It has to do with the effects of urbanization. There's just more pavement, more roof area, more sidewalks, and none of that infiltrates water. And the drainage network can't keep up with all that impervious area. So we're going to talk briefly about urbanization. And what urbanization does from a hydrologic standpoint is it disturbs the soil, And think about if you have soil where the grains are open versus they've been compacted, and how that maybe would affect the amount of water that can infiltrate down. A compacted soil, which has less void volume, is not going to infiltrate water as quickly as a natural soil. A natural soil maybe that has roots that have been going through it. But when you have a more uniform soil that's been compacted, that's going to reduce the infiltration that occurs. If you're removing leaf litter, then you're speeding up how quickly water moves through the environment, because the twigs, the leaf, the little branches that fall on the ground, all that clutter that you find when you're walking through the woods really slows down how quickly the water moves over the surface compared to bare earth or compared to pavement. Water can flow over pavement really quickly, but it can't flow over leaf litter very quickly. And it turns out that the speed that water is able to flow over the surface really contributes a lot to whether there's going to be flooding. If there's fewer trees and plants, that means there's going to be less interception, that the raindrops that fall from the sky aren't going to temporarily be delayed by landing on a leaf. They're going to go straight to the ground. So interception is something that can reduce the speed of peak flooding. And then the other big effect besides these is if you're adding more impervious surfaces like roofs and sidewalks and pavements, all of that stuff is just increasing the amount of runoff and decreasing the amount of infiltration of water into the soil. So if we look at it with a hyetograph, and that's one of the words that's on your vocabulary list, hyetograph. A hyetograph is a representation of rainfall. So look at the vertical axis. On this figure we have both rainfall rate, and so the hyetograph, let me do this. I've just learned a new trick today. See this red dot? Isn't that fancy? So rainfall is this. So let's say, just for instance, there's 3 15-minute periods. So it was raining at this rate, inches per hour, and then the rainfall was higher for 15 minutes, and then the rainfall reduced for another 15 minutes, and then it stopped raining. So the hyetograph is this one that's above, of the rainfall. On the same figure, we're also representing infiltration. And so the top of this curve is what the infiltration, meaning rainfall getting into the soil before urbanization, back when there was leaf litter, there was plants, there was loose soil, lots of water got down underground. But then after urbanization, there's less infiltration. So what is the net effect? Well, the area between the rainfall hyetograph and the infiltration curve is how much excess moisture there is. That is the depth of precipitation that's going to run off. So if we had, for example, 1 inch per hour of rainfall, and then the infiltration rate was only like 1/2 inch per hour and declining during the storm, because infiltration rate gets slower and slower. As the soil becomes waterlogged, it's not going to receive as much moisture. And so that's why there's this declining rate of potential infiltration. So think you've heard the phrase, the area under the curve. So it's the area under the hyetograph curve and above the infiltration curve that is excess. Excess rainfall becomes runoff. Any questions so far? So the effect of urbanization, there's going to be more excess rainfall because there's less infiltration than there used to be. And so there's just more of this volume below the rainfall hyetograph and above the infiltration curve. So that's urbanization from the standpoint of rainfall. And if we look at it from the standpoint of runoff, then it's this other figure where this is a hydrograph. Hyetograph was rainfall. Hydrograph is runoff. So this is a depiction of the water that's coming out of the watershed. And so before urbanization, the peak flow was relatively low, The runoff rate in CFS wasn't as high, and it was delayed. So the two effects of urbanization on the hydrograph is that there's more volume, higher peak rate, and faster time to peak because of the urbanization. More water, and it comes quickly. I guess I'd say those are the two effects. There's more water, and it arrives more quickly, and that's bad for flooding. So that's urbanization. The next few slides are some things that people do to reduce the impact of urbanization. These are best management practices for dealing with excess runoff. So for example, if you have a road and there's a ditch, why not put some grass between the road and the ditch? Because if there's grass, the water will get down into the soil. It could filter out, like if there's sand or pollutants. There can be some biodegradation in the grass, and so they call that a vegetated filter strip. Well, this is just some grass by a road, but what this figure shows is if you had crops sometimes have fertilizer and pesticides that you don't want getting into the natural environment. And so having a grass filter strip would, when there's runoff from the cropland, water could infiltrate into the grass and you could have more of that bioremediation. Same thing if you had a timber area that was on the other side of a road. So sometimes it's not just decorative to have grass and vegetation and trees next to a roadway. It can be a way of creating a barrier between this urbanization and a stream that's carrying stormwater. So vegetated filter strips is one approach. A lot of the runoff here in Huntington that gets into storm sewers or the combined sewer is simply that people have their roof drains connected to the pipes. So the water comes straight from their roof to a pipe that instead of flowing into the yard, the pipe goes down into the ground and to the sewer. And so simply disconnecting people's roof drain from the sewer is going to reduce how frequently you have a combined sewer overflow. And you may remember I was talking about how dirty it is in Four Pole Creek, where we have more than several times a year, the combined sewer is discharging, overflowing into Four Pole Creek. And so the more people you can get to disconnect their roof drains from the combined sewer, the less often there's going to be those overflows of sewage into the creek. That's another strategy. They call them BMP, best management practice. If you just disconnect and have it going to the grass, that's fine, but it can still make its way over the yard into maybe the roadway. And so a way to enhance the infiltration is, instead of just disconnecting the pipe and setting it onto the grass, is if you create a small little pond at the house itself. Not a pond for the whole neighborhood, but if each home just has an infiltration garden where you plant some native grasses and maybe you modify the soil, like rather than having the typical clay and rock soil that I've got at my house, in this infiltration zone, you'd maybe replace it with more sandy soil, or you'd maybe have a layer of underlying gravel beneath that. So modified soil, some grasses, and a barrier to try and confine the flow and have more depth and more hydrostatic pressure forcing the water into the soil. It's just a way of enhancing the infiltration rate rather than having the pipe feed out into the grass directly. Bioretention is similar to vegetated filter strips, and you can see an example of this if you ever go over to the West Virginia Department of Environmental Protection. They have a parking lot at their headquarters with a series of, it looks nicer than this. This just looks like a bunch of weeds, but they have plants where the water from the parking lot, instead of just going straight into a catch basin like we have out behind this building, it's just asphalt going straight to the pipe, and the pipe goes straight to the river. So instead of that, if you had asphalt that goes to a vegetated area, then you're going to get some of the water into the soil, and the plants there will cause transevaporation, which is You know, they're using some of the rainwater for their cellular respiration, and they're emitting some of the water into the atmosphere through evapotranspiration. So bioretention is a good idea, but of course the downside is then you've got less parking area. And it's amazing how much you notice even just when there's snow in some of the spaces. It's aggravating, right? When you're driving around trying to find a space, but, oh, that's a snow space. I can't park there. So the disadvantage of bioretention is that you're losing some of the parking capacity because you're putting in the vegetated area. Have you ever seen something like this where they use pavers instead of concrete or asphalt? Sometimes people do this for their driveways. I've got a friend who recently did something similar. Rather than paving his driveway, he put in gravel and some like plastic, they look like bricks that just kind of help to keep the gravel in place. Porous concrete is pretty interesting. It is, what are the three components of concrete when you make it? There's three main ingredients of concrete, right? What are they? Well, maybe four if you count the water. There's water, cement, gravel, and sand. Okay? So if you just have the gravel, the water, and the cement, then you can get some very unusual, like leaving out the sand. Look at what this concrete does. This is up at the University of New Hampshire. So they're just pouring water, and a normal concrete wouldn't be this thirsty. They're just dumping loads and loads of water, and it goes straight into the concrete. So the water's passing through the concrete. So this is pervious concrete. And so by omitting the sand, what they do is they have like connected gravel. The gravel is connected with the cement, but there's a route from the surface to beneath the concrete. The water can get through it. There's a path. Can you think of what some disadvantages of pervious pavement might be?
So pores, least pores open for water to get in and freeze and thaw.
Freeze thaw would break it apart. Yeah, so you need to definitely have a layer under this of gravel so that when there's water, it gets through and it doesn't have, standing water is death for pervious concrete. And pervious concrete's not going to last as long as normal concrete anyway. It's just not. But you can make it a lot better with putting in a good slope to make sure that it drains, putting in a layer of aggregate underneath. So that's another way to really reduce the C value of a parking lot. Remember, concrete C value may be 0.98 depending on the storm that you're dealing with. But if you had concrete like that, your C value wouldn't be 0.98. I'm not sure what it is, but that looks a lot better than ordinary concrete. A grass swale. A swale is just another word for a ditch. And you could line a ditch with a lot of different things. You could have, most ditches around here are just bare earth or rock, clay. Out west they have a lot of their irrigation and drainage ditches are concrete lined. But if you can grow grass there, then it slows down the speed of the water through the ditch, which is advantageous because the flash flood doesn't arrive as quickly, helps to mitigate, and it's called routing, the effect of delaying the flow and kind of spreading out the peak just through the transit delay. So grass has more resistance to flow, and then the other effect is that you're going to get more infiltration if that grass is there penetrating the soil, creating channels with the roots to allow more water to get down underground. So using grass instead of a clay-lined ditch or instead of a concrete-lined ditch. You can see that here in this commercial area, they've made some efforts to have a low-lying area where water would flow off the parking lot over the grass, and then this is soil modification to promote infiltration at a certain spot. A regenerative stormwater conveyance channel is the idea that instead of having, remember what we're trying to do is we're trying to increase infiltration and slow down the speed of water's movement. We want to slow it down because if we do that, then it reduces the peak at the central location where all of the water is arriving. So instead of having the water just flow down a channel very quickly, if you had a series of interconnected pools, Then this pool has to fill up before the water overflows to the next pool, which has to fill up, then it overflows to the next pool. So this is kind of like a terrace, a series of interconnected ponds that are built along a terrace rather than just allowing the water to flow freely down the surface, which would be very fast. Each one of those little ponds is filled up beforehand, and if you add vegetation, then that's going to enhance evapotranspiration. It's going to help to filter out organic pollutants, maybe limit the amount of sediment that's getting into the downstream creek. So this is just, all of these are brainstorming ways to prevent all of the water from accumulating at a central location too quickly. Some spots are starting to focus on rainwater harvesting. This is especially valuable in arid climates. In Australia, they go to great lengths to make use of every drop of water through rainwater harvesting. Here in this building, we have sort of a vegetated roof. I don't know if you've seen it before, but if you go up on the third floor, you can see the vegetated roof that is over much of the second floor on that side of the building. And they've got some plants. There's limits on how much effect that has, but it's better than like a metal roof connected to a storm drain that goes straight to the combined sewer. The idea here is that some of the water that falls on a vegetated roof is going to be used by the plants, and even if it's not, it has to penetrate down through the soil that the plants grow in before it gets to the underlying drainage network that goes out to whatever's next, whether it's a pond or maybe even straight to the combined sewer. But they look nice. Filtration practices like trying to collect runoff from filling stations, where if you think about the spilled gasoline or oil that may accumulate on the pavement when people are topping up their oil, it's especially important to try and collect runoff from gas stations rather than letting it go straight into the natural waterways. Constructed wetlands are an attempt to capture things like sediment and runoff from like salty roads and organic pollutants. Cattails and aquatic grasses can really do a lot to improve the quality of water that gets into natural waterways. A dry extended detention basin or pond is intended to most of the time be dry, and water would only accumulate here in peak flow conditions on a rare occasion. And we're going to look at the sizing of ponds today, and this is one of the two main style of ponds. A wet pond is the other, where it's intended to have water all the time. It's just that there's some extra storage capacity, so the water level could rise and fall depending on how wet it's been. Okay, so after urbanization, the peak's too high. We want to try and bring it down by putting in a pond. And so the purpose of the pond is to try and reduce the peak flow rate and delay the time to peak. So how much time from when the storm begins to when you see the peak, if you can increase the amount of time it takes, then that's really beneficial. The ponds also reduce pollutants in addition to those other hydraulic effects. And so we're just trying to overcome and ameliorate the effects of urbanization. So you can broadly define the control measures into two categories. Those that are applied at the source that stormwater is generated. So like, for example, putting a green roof on instead of a metal roof would be an example of source control. Or downstream control is when you've taken the water with a pipe somewhere else off-site, and now you're trying to route it through a pond to try and slow it down before it gets discharged to the natural waterway. So depending on where a pond is located, it could potentially be considered source control or downstream control. If it was like a pond that's immediately adjacent to one development's parking lot, then that could be considered a source control pond. An extended detention basin is one that normally is dry. And the way that you can tell it's normally dry is that the perforated riser, this is a pipe with a bunch of holes in it, it's at the bottom of the pond. And so it's going to drain out slowly through the perforated riser, but if there's a huge inflow of water, the pond level is going to rise because the water in is bigger than the flow rate out in this extended detention basin. And so if the water level gets too high, we don't want it to destroy the dam, so you'd put in a spillway. If the water level got so high that even the spillway isn't able to take it all, then there's an emergency spillway over the top, a preferential route for the water to go over the dam without causing scour and damage. But the extended detention basin is one that normally would be dry, and that's what we're going to be sizing today. It's most efficient on like the range of about 1 day is about how long it's going to hold flow. And it could be used for a pond up to 100 to 200 acres. So that would be considered maybe like the maximum size that you'd want. Otherwise, these detention basins just get too large for draining areas any more than that. If they're not well drained, they can be locations where mosquitoes can breed. And so you have to be careful that you don't allow puddles of water to stay there all the time. They need to have careful attention paid to the soil at the bottom of the detention basin. A retention pond, in contrast to the detention basin, look at where the perforations are in the retention pond. So the perforations are up high in the pipe so that there's always water below those perforations. I mean, like, unless there's just evaporation or something. Like if it was a dry spell, the water level may go below the perforations. But as long as water is occasionally coming in, you're going to keep water in a retention pond. So retain is different from detain. Detain means temporary. Retain means on a more permanent basis. So a retention pond will be wet. You'll see that the residence time in this pond is 2 to 4 weeks. So water's spending a lot more time in the retention pond. And so this is better if you're trying to improve the quality of the water. If you want to achieve some sort of biofiltration, then a retention pond is going to have better performance than just a temporary detention pond. So it's removing pollutants. It requires occasional cleaning out because not only is there going to be sediment at the bottom, like sand and gravel, clay, but there's also going to be organic materials that settle to the bottom and have to be scooped up. So leaves that fall into the pond or just other organic material will form a black sludge at the bottom. So because of that, there's a risk of anoxic conditions, meaning in the absence of oxygen, it can form hydrogen sulfide, which is a really smelly, kind of terrible smell. It's also corrosive, but you just have to keep the pond clean. And all right, so the volume of the pond is going to be the difference between what flows in and what flows out. That's how big the pond needs to be. Is big enough to be the area under the curve of the inflow hydrograph, and then the outflow hydrograph is going to be, like less flow rate out. That's the purpose of the pond, is to try and release the water at a lower flow rate than it came in. So you're temporarily detaining the water in this pond just to limit the peak and increase the time to peak. So ideally you'll have the runoff hydrograph at a high resolution, meaning maybe hourly or even a finer time increments than that. So we're going to calculate the volume that flows in during a certain, for example, hour, and then over time calculate the accumulated volume with the difference between the flow in and the flow out. We'll find out what's the pond height at every moment, calculate the flow out with the orifice equation, and then we'll proceed with the next time increment. All right, so you have, I think, a template file that's on Blackboard, and we're going to use that template file to analyze this pond. We're going to say, if we have a pond that's 65 meters by 65 meters, and this is the flow rate that's coming into the pond over time. And we want to find out what would be the peak flow rate out of the pond. If you've got these notes, I changed the outlet diameter from 250 to 300. So make note of that the outflow diameter here is 300 millimeters. Okay, so let's take a look at the template file. Oh, I meant to erase these preliminary things. So 65 meters by 65 meters, you've got that, right? And so that gives us the pond area is calculated just by the length times width. We're assuming that this pond is rectangular, and so as the water level gets deeper, its length and width stays the same, just for simplicity of calculations. In reality, you'd have like a tapered side slope. So the deeper the water is, the pond area would be increasing. So as our sophistication improves on how we model these ponds, we'll take that effect into account. But for now, let's just assume, as shown here in the example, that as the water level gets deeper, the pond area isn't increasing. So there's no side slope to the pond, in other words. Okay, so C sub D is the discharge coefficient for the orifice equation. Let's assume 0.59, and this pond is pipe. The outflow pipe is 300 millimeters. So we've got the pipe area calculated. All right, so the inflow. At 0 time, it was 0 cubic meters per second. Then it was 0.3. Let me make this a bit bigger in case that makes it easier to see. 0.67, 0.81, 0.64, 0.22, and then from there, there's no more flow. So this is like a flash flood into our pond, and this is the flow rate in cubic meters per second. So this is cubic meters per second. The way that we calculate volume in is V is Q times the time increment. So this is Q, the flow rate. The time increment, there's 3,600 seconds in an hour. So it's going to be the flow rate in times 3,600 to convert it from flow rate to flow volume that came in. Okay, any questions so far? Okay, at time 0, how much has accumulated? How much has come in? It's just 0 so far. And so the pond depth, the way that we calculate the depth of the pond is it's the volume that's in the pond divided by the area. So that'll tell you how deep the water is. So the volume divided by the area, and I'm going to anchor the reference to the area so that when I drag that through later, it'll always keep looking at the pond area. Okay, the depth to the centroid, let's take a quick glance at this figure. So the bottom of the pond is here, and the pipe is, the invert of the pipe is at the bottom of the pond. So the center of the pipe is going to be above that by the diameter divided by 2. So if it's a 300 millimeter pipe, in other words, the center line of the pipe is 150 millimeters off the bottom of the reservoir, the bottom of the pond. Okay, so it's going to be 0 for this first one, but later we're going to calculate that a different way. There's no outflow if there's no inflow, and so there was no volume out during that time increment. Okay, so the accumulated volume after 1 hour, it's just what has flowed in. So the accumulated volume is going to be this 1080. So what's the depth at that time? I guess I can drag this down because I had it in the previous slide. So the depth of the water is 0.256. So the depth to the centroid is going to be the pond depth minus the pipe diameter divided by 2. So the pipe diameter divided by 2. Because that is, what's the distance from the surface of the water to the center of the pipe? You remember depth to the center. So let me sketch this on the whiteboard just to make it clear. Here's the bottom of the pond. Here's the pipe that's going out. And here's the water level. So this is H. H is from the center of the pipe to the water surface. So depth, this is the depth. This is 0.3 meters. And this is 0.15 meters. Okay, hopefully that helps to clarify what we've got here for the depth of the centroid. Now, the outflow, we're going to calculate Q is C sub D times the velocity, which is the square root of 2gh. Okay? So the flow out is times the area of the pipe. Okay, so Q is the area of the pipe, anchor that reference, times the discharge coefficient, anchor that reference, times the square root of 2 times 9.81 times H, which is cell F9. And I have to type that in. I can't click on it because my formula is spread out on top of where I would want to click. So I'm just typing in the location of that H. So area, coefficient of discharge, and then square root of 2gh gives us the velocity. That's the orifice equation. Okay, so that is the flow rate out in cubic meters per second, and then to get it from cubic meters per second into the volume, it's flow rate times 3600. So volume is Q times time. And we're doing this in 1 hour increments, so that's why it's 3600 seconds. Okay, so now the accumulated volume at the next time is the previous volume that was in there plus the new water that came in minus the water that flowed out during the previous time increment. Let me leave that up for a moment so that you can think what that means. We're doing a numerical integration here. We're calculating the area under the curve. And so with each hourly time step, what we're saying is how much came in and how much went out and what used to be in the pond during the last hour. So the accumulated volume now is how much was in the reservoir last hour, what flowed in new, and then what flowed out during the previous hour. Okay? Any questions about this? I think with the rest of this, we can just now drag our formulas down through. So you can highlight all of this and drag downward. And I hope I anchored everything right. But this does look like this is headed in the right direction. So now I can highlight all of this and drag it down through. And let's see what's happening over time with this pond. Okay.
What was the equation for volume out again?
Volume out,
Yes.
this last one, it's the outflow multiplied by 3600.
Oh.
Okay, so look, the pond started with 0 water in it. The storm happened and the pond started to fill up, but then the storm stopped and now the pond is draining. So this does make sense. Like from a conceptual standpoint, the pond had nothing in it. The water came up and then the water goes down. Look at the depth. This is the water level in the pond. It goes up, the rain stops, and then it's slowly draining. So the pond is going out. Now look at the flow rate. Outflow from pond. This is the flow rate out. It comes to some peak, and then it's slowly draining as the water level recedes. Okay, we're going to continue this example when we get together on Friday. But what this asked us, like what it said was, what will be the peak flow rate out of the pond? The peak flow rate, the highest flow rate out, so here's the outflow. So the maximum is 0.231 cubic meters per second. So here's the peak flow rate out of pond. And the second part of the question was, how long will it take to drain the pond to 10% of its peak volume? Okay, so what was the peak volume? If we look here at the volume of the pond, the peak was 7244. So 10% of that is, we want to see when is the amount of water in the pond down to about 720 cubic meters. Here's 714, and it took 18 hours. So I guess we could say after 18 hours, the volume of water in the pond is less than 10% of the peak volume that occurs. All right, so we'll pick this back up on Friday because I want to show you how to draw the hydrographs. We'll create the inflow and outflow hydrographs. That's all I have for you today. We're out of time. If I jumped over some part of this example too quickly, I really would encourage you to try and have a look at the video. Make sure that you get this spreadsheet all set up and good so that we can do the hydrographs on Friday. Take care.